Welcome to the AI Research Roundup. I'm Alex. Today, we're looking at a paper from the Hugging Face trending list, published on September 19, 2025, which was about 3 days ago. The standout idea is a single framework that unifies generative modeling, representation learning, and classification, and it even improves CIFAR 10 FID from 2.76 to 2.59 without changing the rectified flow objective. The paper is titled Latent Zoning Network, a Unified Principle for Generative Modeling, Representation Learning, and Classification. And as we will see later, the implications for model training are quite significant. Beyond image generation gains, it delivers unsupervised representations that beat MoCo by 9.3% and SimCLR by 0.2%, and it jointly handles class conditional generation and strong classification accuracy on CIFAR 10. Also, the authors shared a GitHub repo. You'll find training and evaluation code, configs for the AFHQ CAT and ImageNet case studies, Docker setup, and scripts for DDP training. The README walks through data prep, checkpoints, and results folders, plus a model card and MIT license. Models are linked on Hugging Face. On Hugging Face, you'll find LZN weights for AFHQ CAT image generation and ImageNet embeddings, plus quick usage snippets for sampling images and extracting embeddings. No parameter sizes listed. Alright, Figure 1 introduces the core idea. A single shared latent space lets encoders and decoders for images, text, and labels plug together to perform many tasks. Shared latent space means one common numeric space where different data types map to compatible points, so cross-modal routes become simple. The numbered arrows depict example pipelines, such as label-to-image generation and image-to-label classification. The key message is flexibility, because the same components compose into generation, embeddings, and recognition. Alright, Figure 2 explains what makes the shared latent space useful. It stays Gaussian for easy sampling, and it acts as one hub that different data types can share. A Gaussian prior means the points follow a bell-shaped distribution, so drawing new samples is simple and stable. The ovals illustrate that labels and images carve this hub into separate latent zones, which are disjoint regions tied to specific samples. This partition lets encoders and decoders interoperate, because zones line up across data types. So, Figure 3 explains the two moves that make the system work. Latent computation creates zones in a shared space, and latent alignment makes zones from different data types match. Latent computation means the encoder maps samples to anchor points. Then flow matching, which is a learned transport that morphs one distribution into another, partitions the Gaussian space. Latent alignment then synchronizes those partitions across encoders, so generation and classification use the same coordinates. This pairing keeps sampling simple while enabling cross-modal transfer. So Table 1 shows that adding latent zoning inputs consistently boosts unconditional image generation quality for rectified flow, which means the generator becomes easier to optimize and samples look better. Freckett inception distance, a standard realism score where lower is better, drops on CIFAR 10 from 2.76 to 2.59. AFHQ CAT sees lower reconstruction error and higher inception score, while LSUN bedroom improves on most metrics. Celeb AHQ stays roughly similar, which signals dataset sensitivity. So Table 2 reports linear probe accuracy on ImageNet, showing that the learned embeddings are competitive without labels. Linear probe means a simple classifier is trained on frozen features to test representation quality. The method reaches 69.5% top 1, which surpasses classic contrastive baselines like MoCo and SimCLR. Stronger recent methods like Dino still lead, so there remains headroom, but the unified approach already holds its own. Table 4 shows that adding latent zoning boosts class conditional generation on CIFAR 10 without changing the rectified flow loss. The key signal is a lower Freckett inception distance, which drops to 2.40, so synthetic images look more realistic. SFID also improves slightly, and the precision and recall remain steady, which indicates no trade-off in diversity. The CMMD distance falls, and reconstruction error shrinks a lot, suggesting cleaner guidance during sampling. Okay, 2 takeaways stand out. A single Gaussian latent hub with disjoint zones lets the same encoders and decoders handle generation, representation learning, and classification. And it delivers real gains, like lower CIFAR 10 FID and strong ImageNet linear probe accuracy. The broader implication is simpler: shared pipelines across modalities. That is it for this episode of the AI Research Roundup. I am Alex. Thanks for listening.